Hello, my dear. Welcome to IMS GATE Academy. I hope you are all good and your preparation going to be in a right direction. I am Pragyabrat Tripathi, Faculty Department of Mechanical Engineering. Okay, so today we will discuss continuity of the second law of thermodynamics. What is that? See, we already studied that what is the physical significance of the thermodynamics, second law of thermodynamics. That means it gives the qualitative parameter, not a quantitative. It gives the qualitative parameter. That means the process is feasible or not. See, the process is happening or not. The process is happening. If there is heat will transfer from work, heat will transfer in the work it transfer into heat. That is the process is happen. That means during the process this will happening. But that process is feasible or not, that gives the second law of thermodynamics. See, that's why this diagram is very important. This process is, when the first law is switched on, when the first law switched on, the process is happening. That process is happening. But the actually the process will occur or not, that gives the second law. This is very important. Good morning, Thiru. This is very important. That means if heat will, see, the conservation of energy says that energy will transfer, work is transferred into heat, heat will transfer into work. It is not necessary fully or partially. I'm not saying that, but it will transfer. When the transfer during the process, that means process is happening. Hi Atul. That means process is happening, but the actual process is happening or not, that deals with the second law of thermodynamics. That's it. This discussion will already covered. Now, heat engine already covered. Thermal energy reservoir already covered. What is the physical consequence of the thermal energy reservoir? Now we will consider the statement, the two statement of the thermodynamics. What is that? Kelvin-Planck statement. This is very important. Why? Because beta, see, first read. This is as it is. What the Kelvin says that this is as it is. So it is something advanced language. What is that? See, what is the possible, what is the impossible? So it is said that we cannot do like that. That means it is impossible. It is impossible. I am as engineer, we want to the possible. So it is says that we cannot construct a device. That means it is impossible. That means any device we cannot construct. That means it is impossible that operates on a cycle. That means if the device will continuous working, that means if you want that device continuous operating, you must have a cycle. Okay, so must have a cycle. One second beta, must have a cycle. Okay, no problem at all. You must have a cycle. You must have a cycle. Okay, no problem. That means operating on a cycle. We are not talking about the operating on a process. We are talking about operating on a cycle. That means, see, if there is any engine or any device, if you continuous operating, you must have operating a cycle. That means if you want to construct a cycle, that cycle is impossible. What is the condition? The condition is that produce no effect other than the raising of weight, that means work, and exchange heat with a single reservoir. That means you cannot construct a device which take a heat and totally heat will convert it into work without rejecting, without loss of any energy to the another reservoir. That means in this statement they says that if you construct a device, there have a minimum 2 thermal reservoir. That means this gives the information about number of reservoir to operate a device on a cycle. On a cycle. That means what is impossible? What is impossible? The impossible is that means if you want to design a device, okay, which is operating on a cycle, okay, and no effect other than raising of weight, that means work producing, it will work net out, okay, by taking heat from a reservoir, okay. So it says that it is not possible, it is impossible. That means if there is a rejection, if you write that dotted line, no problem. That means if QL is 0, it is impossible. If QL it is 0, it is impossible. That means you cannot construct a cycle. That means you cannot construct a device. That means it says that, what it says that? It is impossible to convert heat, total heat into work. That means it is not possible to convert heat into work. It is possible once lose something. That is the possible. That means what is possible? What is the possibility? The possibility is that means you construct a device, which is operating on a cycle which produce a net work by taking heat from large thermal reservoir and remaining energy will dump into a low thermal reservoir. That will be possible. That will be possible. That means if you design a, this is called heat engine. That means if you define, that means Kelvin-Planck's statement, the information gives the heat engine, work producing device. This gives the work producing device. Yes, Atul, will that will already covered in the previous lecture, but I will give you that will already covered in the starting class. Yes, it is the genuine statement is that. What is the genuine statement? This is very important, Atul. Okay, no problem. I am happy to revise again. See, my dear, the general statement is of the second law. It is gives that all the spontaneous, what is mean by the spontaneous? Natural process. All the spontaneous process have a certain rhythms, that means a certain direction. That means the second law gives the directional constraint, directional ka badhyata, constraint. That means, see, there are infinite number of processes. There are many processes to convert to go from one point to another point. But out of that, the second law, according to the second law, is say that only one process, only which process is feasible or it is helpful for me, it is efficient, that will predicted by the second law. That means second law says that out of all the process, there is a process, there is a one process which is more efficient. That means that we will follow, that gives the more efficient. That means it gives the directional constraint. What is the direction of the process to be followed? That means this gives the, see, direction of the process. This is important. This gives the, see, this is the very simple example so you can understand. But there may be any other than that example that you cannot directly predict. So you can predict by the property known as entropy. So if you find the directional feasibility or not, that will defined by, that will be predicted by the property which is known as entropy. So with the help of entropy, we can say that the process is possible or not. So your question is that what is the general statement? General statement is that this gives the directional constraint. Directional constraints. This gives the directional constant. That means it gives the direction. Yes, energy will conserve, energy will convert from one form to another form, but that conversion, in which form it is efficient, that gives the second law. Okay, I hope it is clear. Now next. So this is the efficiency. Now if you find the efficiency of this engine, heat engine, we know that 1 minus already defined QL by Q. This is the efficiency. Okay, this is the efficiency of heat engine, and this will be, this equation is hold for any process, mind it. It is not necessary this is a reversible or irreversible. That this equation is applicable for any process. Any process. Okay, so this is the efficiency of heat engine. Now next. So this is precisely says that Kelvin-Planck statement. Okay, beta, this is says that Kelvin-Planck statement. Now the second statement, and what is the other thing in that? So this is are the Kelvin-Planck statement. Okay, and now my dear, sometime in the Kelvin-Planck statement I will give you some extra information for that. This is called, that means in this case, see beta, it is possible. What is possible? That means QL is not 0. QL is not 0. That means QL must have. If the QL must have, so efficiency of heat engine will less than 100%. 100%. It is true. Less than 100%. Yes, if this is happening, so this will be quantity which is in the fraction. That means QL by QH is always less than 1. Yes or not? QL by QH is less than 1. So this is also less than 1. So efficiency of heat engine be less than 100%. Okay, less than 100%. Now, if we operate a power plant due to this heat engine is a work producing device, and this will also be modeled as a power plant. So in the power plant, this is there are two temperature limit. One is the source, this is called source, and this is called sink, and source is the furnace and sink is the environment. So source, this is called source. I will write down here, no problem. Why? Because it gives the feel. What is that? So this is your, if you think about the heat engine, let's suppose beta, this is our heat engine. Okay, this is our heat engine. Okay, operating on a cycle. What cycle? We don't know. Operating on a cycle, and we take, this is our a system. Heat engine is our system. Okay, heat engine is our system. This is our system. Mind it. Now it will take a heat from a high temperature reservoir QH, produce a net output, produce a net work, and dump the remaining energy to the low temperature reservoir TL. Mind it beta, this is TH. So what, if we take, this is our system, so this is our system boundary, this is our system boundary, and this is our system boundary. So this system boundary at this point, the temperature is what? TH minus DTH, so that heat will transfer. This temperature at this boundary is TL plus DTL. This is very important. Okay, this is very important. That means for the system, in the system, this heat will in and this heat will out. across which temperature? The temperature is TH minus DTH and TH plus TL plus DTL. This is very important. Okay. Now, so if we defined cyclic integration of dq, what is the cyclic integration of dq? What is the cyclic integration of dq? Please tell me. I don't know the cycle. What is the cycle? It is reversible or irreversible? We don't know. Only the cycle. So this is generally what, beta? This is generally what? This QH is in, that means positive, plus this out. This is cyclic integration of dq. That's means q net. What is this, beta? That means, see my dear, and we always hear QH is greater than QL. It is right. It is right. It may be, this is one possibility. This is one possibility. QH is greater than QL. This is one possibility. One possibility. My dear, each and every line have an importance. Okay, that means this one possibility is greater than 0. That means cyclic integration of dq is greater than 0 for a work producing device. It is clear. And what is happening, another thing we'll discuss. But right now, this is clear. Cyclic integration of dq is greater than 0 for work producing device. Work producing device. Work producing device. Work producing device. Okay, work producing device. Now, what we know that first law of thermodynamics, dq is equal to cyclic integration of dw. We know that. That means what, beta? dq is greater than 0. This is also greater than 0. Yes, this is also greater than 0. That means QH minus QL is equal to W net. This is according to first law of thermodynamics. Okay. So accordingly, we define the efficiency. What output, net output by input, that means QH. What is the net output? QH minus QL. So it is 1 minus QL by QH. And this is defined for any type of cycle. We cannot stick with the reversible or irreversible. So this equation is valid for any type of cycle. Right. If we think about the power plant, this high temperature reservoir, my dear, this high temperature reservoir is called, this is your source. This is source temperature, and in the source temperature, if you think about the power plant, that means steam turbine, Rankine cycle, we'll discuss later on. This is furnace. This portion is furnace. This portion is furnace, and this is QL. This is your sink, and this will act as a environment, a surrounding, right? Environment, okay? Environment, okay? So this precisely we will use the concept of power plant in the power plant, okay? when we enter into the entropy chapter or your Carnot cycle, we will discuss now today's Carnot cycle. Then we define the cycle is reversible, and what with the reversible, internally, externally, all the things we will discuss, no problem. So this is the things, okay? This is clear. This is the things, okay? Now, Clausius statement. What is the Clausius statement? My dear, Clausius statement gives that, what is that? It is gives the information about heat pump and refrigerator. It gives the concept of heat pump and refrigerator. What is say that? See beta, I give you one thing. What is that? See, if you want, see, this is a high temperature thermal reservoir. See, first see the motivation. This is a low temperature thermal reservoir. Okay. Now, if you connect with the dithermic wall, heat must be flow from high temperature reservoir to low temperature reservoir. There is no any problem. That means this is a spontaneous process. It will be there. That is called a spontaneous process. That means if you attach this high temperature and this is low temperature and attach a metallic wall, you can say that the heat will flow. So this is a spontaneous process, natural process. Spontaneous process. It will occur. Now, but Clausius think that what happen if we take same thermal energy reservoir TL and TH, and we want that heat will transfer from this one. Heat will transfer from low temperature to high temperature. Not possible. This gives the Clausius statement. This gives the Clausius statement. That means it is impossible for any device that operates on a cycle and produce no effect other than the effective transfer of heat from low temperature body to a high temperature body. It is impossible. That means if you want to transfer a energy, a heat from low temperature reservoir to a high temperature reservoir continuous in a cycle, you must have a external agency. Without external agency, you cannot reach them. Same thing. If you draw the water, if you take the water from low reservoir to a high reservoir, you must have a pump. Without pumping, without external work, you cannot able to transfer a water from low reservoir to high reservoir. Same thing is that. Here is the pumping of heat, and in that place pumping of water. That means we want the heat will flow, and at that point we want the heat, water will flow. So if water will flow from low reservoir to high reservoir, it is not a spontaneous process. There must be some external agency known as pump. Same in the case of if you flow the heat from low reservoir to a high reservoir, thermal reservoir, there must be external agency. That means what we will do, we construct a device. Here, we construct a device which is operating on a cycle. So this is impossible. What is possible? What is possible, beta? The possibility is that if this is your low temperature reservoir and this is your high temperature reservoir, and if you want to transfer a heat from low temperature reservoir to a high temperature reservoir, from a low temperature reservoir to a high temperature reservoir, you construct a device which is operating in a cycle in which we have to give the external energy. That means we have energy, external work. That means this will work in. That will assure you it will transfer energy from low reservoir to a high reservoir. This is your QL and this is your QH. That cycle is possible. That cycle is possible to pump the heat from low reservoir to a high reservoir, which is cycle that continuous working. But the problem is that if we don't have this one, if this is 0, if this is 0, impossible. 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 Now, if we want that the lower, if we want to maintain the lower temperature, in that sense, this device is refrigerator. If you want the high temperature maintained, that is heat pump. So, what is the observation here? What is the observation here, my dear? What is the observation here? Right. If you maintain light, right, that means work input device, refrigerator or heat pump. So, work input in a cycle, okay? So, if we maintain low temperature, that is your refrigerator, and if we maintain high temperature, that is your heat pump. And if we maintain the low temperature, that means this is our low temperature, and you maintain this one. So, you continuously extract a heat from this one, QL. It is necessary. If you maintain this space is colder, you continuously extract a heat. That means what do you constantly extract the heat to maintain the low temperature reservoir, that is called refrigeration effect. Refrigeration effect. That is called refrigeration effect. And what is this one? Sometime in the layman language, we can say that what we want. What we want. This is also what we want. Okay. So, this is a refrigeration effect. So, this is a refrigerator. If we maintain the high temperature, that means if this is your high temperature beta, and you maintain this one, high temperature you maintain, If you maintain this one, thank you, sir, thank you. If you maintain this one, high temperature, continuously you give the heat into this. Continuously given. If you maintain a high temperature, continuously you dump the heat on the high temperature reservoir. That is QL. So this QL is a pumping effect. This QL is a pumping effect. This is your refrigeration effect. This is your pumping effect. Pumping effect. And that pumping effect is also sometimes called what we want. What we want. So beta, in the work input device, there are two types, refrigeration and heat pump. In the refrigeration, we want the low temperature, and in the heat pump, we want the high temperature to maintain. And to maintain the high temperature, if you supply the heat to the system, that is called pumping effect. If you maintain the low temperature, you continuously extract that, that is called refrigeration effect. That means in both sense, we have to do a coefficient of performance, COP. We define the performance. What is the performance? See, there is a difference between efficiency and performance. Efficiency is output, net output by input. Performance is what we want and what we pay for it. This is very important. So performance is what? Performance is what we want, divided by what we pay for it. What we pay for it. This is very important. What we want and what we pay for it. What we want, beta? In the case of refrigeration effect, what we want? QL. What we pay for it? Work in. In the heat pump, what we want? QH. This is QH, not QL. QH. And what we pay for it? W in. So this, accordingly, this you can define the coefficient of performance. We already covered this thing. Okay. So this is your Clausius observation. This observed by the Clausius. My dear, so this is a spontaneous process. You cannot reverse back spontaneously without any installation of device which is extract a energy from the external source. That will be a second law. That means second law says that it is not possible. This is possible naturally. There is no any science. Naturally it is possible. But if you want the direction reverse, it is possible or not, that gives the second law. That means this gives the direction, in which direction it is possible. Okay, so we have to design, there are two devices. One is power producing, other is power absorbing. So Clausius statements, according to the Clausius statement, we design the power absorbing device, that means power input cycle, and for the Kelvin-Planck statement, we design the power output cycle. So there are two types of cycle, power output cycle and power input cycle. Power output cycle known as heat engine, power input cycle known as refrigeration or heat pump. Okay. Now, next one is, so in this condition, this high temperature is your source, yes or not? Is your source now? This high temperature is your source, yes or not? This is your source. It is visible, it is your source. Okay. This is a source, and that source is a sometime called warm environment. Which environment? Warm environment. That means warm environment. Okay, and this is called sink, low temperature, and that is sometime called cold space. Cold space, sometime called cold space. So the terminology is very clear. Why? Because why we study the importance of this study to implement this concept into a power plant. That is very important. So these terms are very important. Warm environment, cold space, environment, furnace, like that. Furnace act as a source in the case of heat engine. Warm environment act as a source in the case of refrigerator or heat pump. Okay, so this type of terminology have to very clear about that. Okay, now if we apply the cyclic integration, this is very important. This is very important, like that. See, if we apply the cyclic integration of dq for the power producing device, there must be greater than 0. This is very important, I am telling you. But if we installed a refrigerator or heat pump, what is delta Q? See this, my dear. See this, my dear. That means this is very important. That means if you design a device, not red color. What is this? This is okay. Okay. Device. This is either, let's suppose this is a refrigerator. Let's suppose refrigerator or heat pump. Let's suppose operating on a cycle, and let's suppose this is our system. Let's suppose this is our system. Okay, let's suppose this is our system. This system will continuous work on a cycle. The clauses state that the possibility is that when you take energy, then we are able to extract a heat from low energy reservoir and dump the remaining energy to the high thermal reservoir. That is okay. Now, so what is this temperature? This is our system now. So what is this temperature? This temperature is TH plus DTH, so that heat will out. And this temperature, what is this temperature? TL minus DTH. Yes or not? So that heat will travel. Now beta, this is very important. This is called source. High temperature always called source. This is low temperature always called sink. So in the power producing, sink is called, what is sink is called? Right now sink is called warm environment. Warm environment. Source is called cold, warm. This is cold space. Sorry, this is your cold space. Sorry, my dear. This is called cold space. Cold space, and this is called warm environment. Okay, this is called warm environment. Now, this, from low temperature, but this is not direct heat transfer. Okay, what is that? What is Atul? What says that? Yes, this is QH. Thank you. Now, what is your question? I don't understand. 1 second. One second. Thank you. QH. Atul says that, but this is not direct heat transfer. Which one, Atul? Just this one, I think. You telling this one, please? But this is not direct heat transfer. Yes. From low temperature reservoir to high temperature. From low temperature reservoir to high temperature, we cannot directly heat transfer. We have to install a cycle. Very important. You cannot. We have to install a device. Which type of device? The power absorbing, like that. See, produce no effect other than the effective transfer of heat from low temperature to high temperature. That means if you know any effect will take from the outside to pump the heat from lower temperature to high temperature, it is not possible. Yes. So what is the possible? You construct a device. Okay, I think you are asking like that. Okay, I think I will what is there any confusion in this contest? Yeah, other thing you want to ask, please reply in the chat box. Okay, it is clear, then okay, otherwise you can ask me. Okay, repeatedly, no problem. Okay. No problem. So this is our refrigerator source and this is our work absorbing. Now if you find the cyclic integration, what is the cycle integration dq? What is the cycle integration in this case dq? The cycle integration, we know that this is QL in positive plus, why? Because this is summation, minus, it is out from this system, Q minus H. Okay. See the beauty. It is one possibility that QH always greater than QL, yes or not? Yes or not? So QH always greater than QL, that means the possibility is that this may be less than 0. Very important. This may be less than 0. Other equality or inequality will also hold, but that inequality we will search in the next session. Okay, next classes. Okay, what we will then. Accordingly, cycle is reversible or irreversible. Okay, so cyclic integration dq less than 0 for work absorbing device. That means Calvin Planck, in the Calvin Planck statement, cyclic integration of dq greater than 0. Clausius statement, cyclic integration of dq is less than 0. This is sure. This is sure. So we have to think like that. If you take one observation, what is that? Cyclic integration dq is greater than 0. Cyclic integration dq less than 0. Cyclic integration at dq greater than 0. This greater than 0, work producing. That means this is or work producing, and this is your work input device. This is clear. Okay, so this is very clear. Why we are discussing this thing? Why? Because in this manner you cannot teach anywhere. I am damn sure that in this manner you cannot teach anywhere in the sense of second law of thermodynamics. This gives the builds up of the quantity dq by t, and that quantity is a very much important quantity. Why? Because this quantity is related by dq by t, and that dq by t is related to the property, and what property we will discuss in the upcoming classes. Okay, so be patient. So this is your work absorbing device. Okay, so work absorbing device dq cyclic induction dq less than 0, work producing dq cyclic induction dq greater than 0. Okay, no problem at all. Now the next one is the very important, very important. What is that? What is the contest? Ah, yes. This is very important, I'm telling. See, from here, my dear, there is one punch. What is that? Okay. There is a one term reversible cycle. Okay. Okay. If we think about the reversible cycle, first thing come into mind, ki sir, what is the criteria for the reversible cycle? Yes or not? What is the criteria for the reversible cycle? Okay, 1 second. What is the criteria for the reversible cycle? See, reversible, the word reversible, that means total reversible. Total reversible of the system. What is the total reversible? We already discussed the total reversible is the combination of internal reversible plus external reversible, right? Now the important thing is that how to make the system is internally reversible and how to make the system is external reversible. If you make the system internal reversible, this is very important. If you make the system is internal reversible, if you make the system is internal reversible, there must be a quasi-static process. This is very important. It must be a quasi-static process. Must be a quasi-static process. That means you can say that sir, there is no any dissipative effect. No any dissipative effect. This is very important. That means no any dissipative effect. That means there is we cannot change the property in terms of temperature due to the viscosity or the friction. That means friction and viscosity are negligible. See, internal reversible is due to the dissipative effect. This is very important. Internal irreversibility, internal irreversibility. If you say that internal irreversibility, that means if you want the internal reversible, you disregard the dissipative effect. That means when the piston cylinder, if you assume that when the piston is moving inside the cylinder, you must have a no friction between the cylinder wall and the piston. When we cannot consider, when we are able to cannot consider there is no any friction, when the process is very slow. When the process is very slow. That means each and every point during the process have a locus. That is called no any dissipative effect. So must be a quasi-static process. Now, what is the external reversible? The external reversible, that means, this is very important, How to make external reversible? How to make external reversible? So, external, internal due to the dissipation, you search as a dissipation, internal, internal as a dissipation, external as a heat transfer. So, external reversible or irreversible, you check the heat transfer through which range of temperature. Internal reversible or reversible, you check the how much the process will, how quantity the process have a dissipative effect. It is more dissipative or very minimum dissipative. If there is a very minimum dissipative effect, it may be modeled as an internal reversible. That means externally reversible, that means heat transfer through infinitely small temperature difference. A small temperature difference. That means infinitely small temperature difference. That means in this sense, if you want the external reversible, delta T tends to 0. This is very important. Delta T tends to 0. That means heat will transfer from the surrounding to the system. The temperature difference is very minimum. If you do like that, then you can say that, sir, this is the external reversible. Number first. Now, if we want, so in the Carnot cycle, that means there is a cycle known as Carnot cycle. What is the major perspective of the Carnot cycle? The major perspective of the Carnot cycle, it is a total reversible. That means internally it is a quasi-static process, no dissipative, and also heat transfer across a finite temperature difference. Sorry, infinite temperature difference. Heat transfer across a infinite temperature difference. Okay, this is clear. This is clear. Total reversible. Now, so there is a cycle, and this is your cycle. Yes or not? This is your cycle, and cycle have a many process, more than 2 process. Okay, minimum 2 process. That means what the cycle will constitute? Minimum 2 process. So in the Carnot cycle, there are 4 process. This is your 4 process. Okay, in the Carnot cycle, there is a 4 process. What is that? We'll discuss. See, first, there are 4 diagram here. The first one, we discuss the first one. This is, first is the adiabatic compression. My dear, we'll start the process 1 to 2. This is very important, okay? Process 1 to 2. What is the process 1 to 2? There is a compression. What is that? Compression. That means you compress the gas. You compress the gas in a closed system. This is the closed system, beta. Okay, you compress the gas. So for you make a closed system, there must be a piston cylinder arrangement. In that piston cylinder arrangement, there is a gas, a fluid, which have to compressed, and compression you want that adiabatic. That means we know that when we compress anything, its internal energy will increase. If internal energy will increase, internal energy is a strong function of the temperature. So there may be chance of increase the temperature. Okay. So in this condition, if the temperature will increase, the system is heated. If the system is heated, the system the heat within the system, the heat want to transform from the system to the surrounding, but you are blocking. That means you design a wall of the cylinder in such a way, strong wall, in such a way that is a adiabatic wall. That means adiabatic wall is a kind of a wall which doesn't allow any type of heat or thermal stresses. That means in this case, heat transfer during the process 1 to 2 is 0. Okay, this is the adiabatic. 1 is the start to the compression, 2 is the finish to the compression. And during that, there is an adiabatic compression, number first. And you know that during the compression or expansion or anything, we say that the cycle is reversible. If the cycle is reversible, that means it is a total reversible, internally or externally. That means you compress reversible adiabatic. Reversible plus adiabatic. And what is the nature of reversible plus adiabatic? This is a very important nature. We'll discuss in the next session. But we know that the adiabatic, there must be any chance of heat transfer. That means you have to design, my dear, that means you have to design a cylinder such that okay, this is our piston, and this is our system. Okay, this is our system. Okay, this is our system. This is our system. Now you design a cylinder in such a way there is a completely insulated. That means there is no any chance of heat transfer. Now you compressed it. Okay. Now you compressed it. Okay. Now you compressed it. Now you compressed it. Okay. If you compressed it, what happened? There is no any transfer of heat. There is no any transfer of heat. That means heat transfer 1 to 2 is 0. That means if you compressed it, its continuous temperature will increase. Yes or not? Its continuous temperature will increase. Now, so you compress from point 1 to point 2. That means in this case, you must have a work in. And which type of work? Displacement of a boundary. That means piston want to displace the system boundary. That means from the surrounding, piston acts as a surrounding. From the surrounding, the work will done on the system. Okay. So this is your adiabatic compression. Okay, beta. This is your adiabatic compression. Okay, no problem at all. This is your adiabatic compression. So in this case, piston will move down. Piston will move down up to 0.1 to 2, let's suppose. So this is adiabatic compression. Now, what will done? Slow compression. This compression is very slow. Slow compression. Okay, slow compression, very slowly. Why? Because we want that the internal reversible as well as external. There is no any chance of external irreversibility. Why? Because there is no any heat transfer, but it is internal reversible, so that it is a slow compression. Why we want a slow compression? Why? Because we want that internal reversible. Okay. So we want a slow, very slowly compression and reach at 0.2. In this sense, temperature will increase. Why? Because there is no any chance of heat transfer. So this is a step number 1, process 1 to 2. Now this is first process. Second process. What is the second process? Process 2 to 3. Process 2 to 3. What is process 2 to 3? Now, if we compressed it, my dear, if we compressed it, its system temperature will increase. That means it stored more energy as compared to first. That means at state point 2, the energy of the system is more as compared to 1. Why? Because you add the work in the system. So it will ultimately increase the energy. That means in this system have increased energy. Now in the second step, you are remove all the insulated things and you want to allow the heat from the system to the surrounding through a very infinitely small temperature difference, so that external it is reversible. That means see, this is a compression. First is the compression. Now if you compressed it, slow compression, if you want that the slow compression, it will compress it, there is no any heat transfer. Now process 2 to 3 is isothermal heat addition. Now we add the heat. That means temperature. Why? Because see, when we compress this, its temperature will increase. Add the heat. If you think about the engine, you supply the fuel, so that fuel will burn. So we add the heat. So in this process 2 to 3, heat addition. Heat addition. Now this is at point 2. Now when the heat will add, the system will expand. That means 2 to 3, heat will add, and mind that the heat addition, see, reversible isothermal process. Reversible isothermal. That means you add a heat as a reversible isothermal. That means you cannot increase its temperature. How? See, when there is a system and we add the heat to the system, temperature will increase. But you don't want to temperature will increase, immediately you expand the system. So its temperature maintain same. Now again your heat will supply, again the system want to increase its temperature, again you expand. So expansion like a quasi-static and addition like a infinitely small temperature difference. So expansion like a quasi-static and addition of a heat through a very infinitely temperature difference. So it is a total reversible. That means if you want that, this is our system. One second. No, it is not like that. Not it is 1 second beta. Delete this one. It is or not? No, no problem. See, what is that? You want that this is a position number 2 of the piston, yes or not? This is number position 2 of the piston, yes or not? This is at a 2 of the piston, okay? This is 2. Now, here, you remove all the, so this is the temperature T at any time 2. Now, and this is your high temperature, mind it. This is a very high temperature TH, let's suppose. So, what is that? It is visible or not? No, it is not visible, okay? No problem at all. Next page. What is that? Process, this process continue with that. This is your cylinder, okay? This is your cylinder and this is your piston, okay? At this point is position 2. Now, you take a thermal reservoir which have a high temperature TH, you transfer, this is your system boundary, you transfer a heat from high temperature reservoir to a low, and that low temperature, it is your nothing, it is TH minus DTH, across which the heat will transfer. So that the system will expand and it will reach at this point. That means there is a expansion. That means the system will expand. Expansion 2 to 3. And during that, temperature is constant. TH. This is, let's suppose DTH is tends to 0, reversible. So TH is constant. That means while you transferring a heat, the temperature will increase, but accordingly you push the piston upside, so the temperature maintain constant. Again you supply a heat, temperature again want to increase, you again push the piston up, so that the temperature throughout the constant. So this is your 2 to 3 is nothing, is a reversible plus isothermal process. Okay? Reversible isothermal process. Now, once it is reached at a point 2, at the top point 3, the third process. What is the third process? The third process, what is that, beta? See, you continuously supply a heat and accordingly the piston will expand. Piston will expand. Now, when it will expand, you want immediately put back. Very important, this thing is very important, third line. Put back. That means it is, this is your cylinder, this is our piston, beta. This is our piston and this is our cylinder, let's suppose. So this is a point 3, okay? So this is expansion, and expansion at a constant temperature. Now put back insulation. This is very important. What is happening in this situation? Put back the insulation again and keep on expansion. Keep on expansion. Keep on expansion. That means expansion is going on. Okay? Keep on expansion it slowly. it slowly. Okay, so this is what beta? Reversible. Slowly it is reversible and put back insulation, that means adiabatic. In this condition, that means what is happening, if this is our cylinder, this is at a point 2 of a piston, it will move slowly at this point. This is 3, so this is also expansion. Now 2 to 3, now 3 to 4, during 3 to 4, the piston will reach at 3 to 4. In that situation, there is also slow expansion, but the 3 to 4, during the 3 to 4, there must be an insulation. That means during 3 to 4, you have a insulate all the things, and automatically the piston will raise at the final position 4. So in this situation, 3 to 4, we insulate, that is put insulation. So beta, there are two nature of the expansion. One expansion at a constant temperature, one expansion as an adiabatic. So adiabatic expansion, what is the adiabatic expansion? You store the energy, that means you supply the energy continuously. You just move the piston. Once it is start to movement, you disregard this heat transfer, put the insulation and go automatically movement. That means this 3 to 4, this is very, very important. This 3 to 4, this 3 to 4 gives the power stroke. This gives the power stroke. Power stroke. This is the actual power output. In this sense, the power will out. This is the power output, power stroke. So 3 to 4 is the power stroke in which we cannot do anything. The piston automatically move and it will output. Why? Because piston will be moving, that means boundary will displace, so it will out the work. That is called power stroke. So there are two expansion. There are two expansion now. First is isothermal expansion. Why we want the isothermal expansion? Why? Because we start the piston to move at a constant temperature. At a constant temperature, you add a heat, and once you add a heat, you are put back insulation on the piston, so that what the addition of heat, that heat will require that energy, what you add the energy in the cylinder, that energy want to push the piston at position 4. That is, in the case of 1 to 2, you cannot supply externally. So this is adiabatic expansion. So one is the isothermal expansion, other is the adiabatic expansion. Okay. So this is a process 3 to 4. So 3 to 4 is reversible plus adiabatic expansion, and this is your reversible plus isothermal expansion. You write expansion, process expansion. So this is also expansion, this is also expansion. Okay. Now we take the process 4 to 1. Process 4 to 1. 4 to 1. See my dear, this is 4 to 1 process. Adiabatic compression 1 to 2. Isothermal expansion, right? Isothermal expansion. So there is a one expansion, there is another expansion. So this this is what adiabatic compression. This is 1 to 2, like that. This is your 1 to 2. This is your 2 to 3. 2 to 3. This is your 3 to 4. And this is your 4 to 1. Yes or not? Yes or not? Yes or not? Okay. So 1 to 2 adiabatic compression, 2 to 3 isothermal expansion. We add the heat. See, hot reservoir, we add the heat in this sense. Now 3 to 4, there is a adiabatic expansion. You already expansion. So work out. Here work out. Yes or not? This is work out. Now, so this is a 4 to 3. Now 4 to 1, this is isothermal compression. Now, if this is our system, now for process step number 4, that means process 4 to 1, you just uninsulated and put the reservoir and compress it and transfer the heat at isothermal. That means once you compress it, its temperature will increase. Immediately, you want the temperature is constant, you reject the heat from a low temperature reservoir. So the temperature remains constant. So this is a reversible isothermal compression. So there are 2 compression and 2 expansion. 2 compression is the isothermal, 2 expansion is the adiabatic. So process 4 to 1 is reversible plus isothermal compression. So this is also compression. Okay. What we will do, if this is our piston cylinder and this is at 0.4, okay, this is at 0.4 and this is our system. This is our system, and we achieve at this point 1, 4 to 1. So there must be a compression input. Okay. So how it when and the compression T is equal to constant. That means if you compressed it, its temperature will increase, but you don't want the temperature increase, heat must be reject. Heat must be reject. And rejection must be temperature less than the system temperature. That means at this boundary temperature of this system is TL minus dTL and the surrounding temperature is TL, so that the heat will transfer QL. So this QL at constant temperature and this dTL is tends to 0. Why? Because external reversible. That is external reversible. Okay. So the temperature remains constant. That means in this case heat will reject. That means heat rejection. Heat rejection at temperature constant. TL is constant. Lower temperature. So the cycle will complete at 0.1. So if you draw reversible, so this is a slow compression. 4 to 1 slow compression. Okay, slow compression. So that why the slow compression? So that it is internal reversible as well as external reversible. That means if you draw the PV diagram of this one, if you draw the PV diagram of this one, this is your pressure, this is your volume. Okay, Okay, this is your pressure diagram, and this is your volume diagram. Okay, beta. So this is your pressure P, and this is your volume V. Now, step number first is what? Reversible adiabatic compression. Okay, so if you apply the first law of thermodynamics, Q122 is equal to U2 minus U1 plus W122. Okay, so in this sense, the compression and compressor reversible adiabatic, so this is 0. That means what is the work? 122 is equal to minus of delta U. That means this is a work input. So if you compress, pressure will increase, volume will decrease. So it is look like that. This is your isothermal compression. This is your isothermal compression. This is your isothermal compression. Okay, temperature in this condition, the temperature is constant. This is T L. Okay, this is your TL. Not this, not required. Okay, one thing is that we'll just erase this one, no problem. But not like that. It is look like that, beta. This is look like that. From start from here, 1 to 2. Okay, this is a 1 to 2. That means 1 to 2. Start compression. So this is reversible adiabatic. So start. This is 1 to 2. It is not a constant temperature. So this is 1 to 2. Let's suppose this is 1 to 2. So this is the adiabatic compression. 1 to 2. What is 2 to 1? Adiabatic compression. What is 2 to 1? Reversible isothermal heat addition. So if we heat will add, there must be high temperature. That means addition of heat from where? From high temperature. So there must be a heat in it. So there must be an expansion. That means there must be an expansion. There must be a expansion. Okay, 1 to 2. So and 1 to 2 and 2 to 3. This is adiabatic. So the PV. This is very important, beta. What is the slope of adiabatic? That means if you want the slope, this is very important. dP by dV, the slope is higher for the adiabatic. At adiabatic is gamma times of the slope of dP by dt of isothermal. dP by dV at temperature constant. So isothermal slope is higher as compared to adiabatic. Okay, that means if you write adiabatic and if you write isothermal, so this is gamma times. Now this is your adiabatic compression. Adiabatic compression. And this is your isothermal. This is your isothermal expansion. This is your isothermal expansion. Okay, this is your expansion. Yes or not? So this is 2. This point is 2. Now there is an adiabatic expansion. This is a compression, isothermal expansion, again expansion. This is again isothermal expansion. This is isothermal compression. This is isothermal expansion. So 2. This is 3. Now there again there is a, this is a compression, isothermal expansion, again adiabatic expansion, again there is a compression, And which compression? Isothermal. Again, there is a isothermal compression 4 to 1. Isothermal. So it is look like that. 1 second. 1 second. We'll draw the. This is very important thing, so that I will discuss here. This is arrow put like that. The slope of this line and this line is same. So this is like that. Okay, this is like that. So this is 4 and this is 5. Okay, remove this one, no problem. Yeah, 4 and this is 1. Not this is 1. Okay, so this is look like that. Okay, so 1 to 2 compression, expansion. So compression and expansion are same slope. This is the adiabatic. Isothermal compression, isothermal expansion. So this is your TH, high temperature, and this is your TL, low temperature. Right? These two lines are reversible adiabatic. These two lines are reversible adiabatic. Okay, reversible plus adiabatic, and these two lines reversible plus isothermal, and this gives a clockwise rotation. That means this is work net. And what is the area in this one? What is the area in this one? What is the area in this one? That area gives the net work. That area gives the W net out. That gives the W net out. So 1 to 2 reversible adiabatic compression, 2 to 3 reversible isothermal expansion, 3 to 4 reversible adiabatic expansion. So 2 to 3 expansion, 3 to 4 expansion, 4 to 1 compression, 1 to 3 compression. 4 to 1 compression is isothermal compression, 1 to 2 compression is adiabatic compression. So there are 2 compression and 2 expansion, and both 2 compression is, one is isothermal, one is adiabatic. Both 2 expansion, one is isothermal and other is adiabatic. Okay, so now we will discuss these things in detail in the next upcoming chapter. Okay, and we will calculate also what is the TS diagram on the entropy diagram once we start the entropy principle. Okay, up to that, thank you, bye bye.